Today we're starting on chapter 11. We'll be looking at a review of some basic concepts of perimeter and area to get started. So we have some basic shapes here that we should know how to find areas of, and we'll talk about those in our notes here. So one thing to talk about as a beginning is the idea of perimeter versus area. So perimeter is the sum of all side lengths, and it's measured in linear units like meters, feet, inches, etc. Whereas area is the space inside of a shape. So perimeter is going around the outside of the shape and measuring a line. Area is measuring the inside of the shape, and it's so I don't like using area in the definition of area, but the area inside of a shape, and it's measured in square units. So we measure it in square inches, square meters, etc. And so if we have a shape, the perimeter is just all of these line lengths added together. So if we have 2 plus 5 plus 4 plus 3, then our perimeter is going to be equal to 14. And let's say these are all in inches. Then we're going to have 14 inches as our measurement. We typically write the perimeter below the shape. That's how I like to write it. And then inside of the shape, we write the number that represents the area. So I don't know what the area of this shape is, but let's just say that it's about 16 square inches, right? We haven't fully defined or constrained the shape because we don't have any angle measures. So we'll just pretend that it's going to be 16. That could be reasonable, maybe. So that's how we show area, and we write it as square units rather than linear units. So hopefully that's a good reminder of that. And now we want to talk about the areas of some basic shapes. Perimeter is kind of uninteresting because it's always just the sum of all of the side lengths. So no matter what kind of shape you're dealing with, other than if there's curved edges, but for any kind of polygon, perimeter is just addition. You're just adding up all the sides. So we're going to talk about some basic shapes, and we start with the square because the square is kind of the fundamental idea of how we measure area in the first place. So if I have a square that's one by one, so say I give it units, why not? Say this is 1 centimeter by 1 centimeter, then the area is 1 centimeter times 1 centimeter, and that basically is filling in this box. So this little unit, this little square unit, is 1 square centimeter, and that's how we measure the area of any shape, is in these little squares. But sometimes it's not an even number of squares. So the one that's the next step up, that's the most simple, is a rectangle. A rectangle has 2 dimensions, whereas a square only has 1. It just has a single side length. A rectangle has a length and a width, or a base and a height, either way. So we'll call this the height and this the base. And we could take that base and say the base is, say, 4 meters, and the height is 2 meters. We can think of breaking this rectangle down into little squares. So 1, 2, 3, 4. So we broke this 4 down into 1, 1, 1, and 1. And then for the height, we break it down into 1 and 1. And then each of these represents 1 square meter. So we end up just multiplying the length of the base times the length of the height. So we end up with the area is just the base times the height. So we get kind of the next step up, and everything else is going to be based on a rectangle. So from squares to rectangles is a pretty easy step forward because we're going from just one little square to a series of little squares, but they all still line up really nicely. So the next shape we'll look at is a triangle. A triangle, the way we want to, well, actually, no, we're going to go to parallelogram next. We need parallelogram first. So a parallelogram is basically just a rectangle but slanty. So if I have a rectangle and I slant it like this, then we can basically think of it a couple of ways. One way is that if we remove this part, then it's exactly the same size as this missing part right here. So I could take that extra triangle over here and put it on the left, and now this would just become a rectangle that has height h, and this is the base length. We know that for a parallelogram, the bases are congruent, so basically we're just creating a rectangle from a parallelogram. The other way I think of it is like if I had a deck of cards and I stacked them up, and then I like kind of offset it so that each card is a little bit over from the last one, then I end up with a shape that basically looks from the side view like a parallelogram. And I could come in and just easily square these up by pushing them together like a stack of cards or stack of paper and make it straight, and then that profile would just become a rectangle. So parallelogram is also base times height, just like a rectangle. Next, we're going to look at a triangle. So a triangle is fundamentally half of a parallelogram. So any parallelogram that we can draw, if we add in a diagonal, we always create two congruent triangles. So we've looked at that extensively with congruent triangles and proving that these are congruent by transversals and stuff. So we know those are congruent. So whatever this parallelogram is, we have the height right here, and then the base is that base of the triangle. So we end up with just half of that. So a triangle is 1/2 of a parallelogram. And depending which altitude we want to draw, so I drew this altitude from this base, but we could split, let's go back. We could split the triangle or the parallelogram this way, and now we would just be changing our reference of what the base is and what the height is. So well, I can still use the same base and height, but the idea is I can go to the other sides and use this as the base, and I can use the height as being, let's not. It's simpler just to think of it in this orientation. So, but you can create any triangle. So if you just draw a random triangle, and you take that triangle and reflect it over one of its bases, you can create a parallelogram. So we kind of saw that when we were dealing with quadrilaterals and dealing with a missing coordinate for a parallelogram. So we could create 3 different parallelograms from this triangle. So what I was trying to say here is you could split that parallelogram different ways and create your triangles. So depending which side I reflect it over, I get 3 different versions of that parallelogram. But the takeaway is we have 1/2 base times height is the area of a triangle. Then we have other quadrilaterals like a trapezoid and a kite and a rhombus, and all of those you can think of as being just a combination of triangles. So I think let's look at kites next. So a kite can pretty simply be visualized. Actually, should we do rhombus next? I don't know. We'll draw a kite. Rhombus and kite are really similar, as we know they kind of belong to the same family. So a kite is basically 2 triangles stacked on top of each other. But then we could even say it's 4 triangles, where we have 2 sets of 2 congruent triangles. So the way to think of a kite or a rhombus, since a rhombus is a type of kite, is based on these diagonals that are dividing the shape into triangles. So if we look at just the top half, so just this upper 2 triangles, then this is going to be, let's call this length A and this length B, and then this length C. And then we'll refer to it as its diagonals a little later. So my top triangle is 2 C's, that's the base of the triangle, times A, the height, divided by 2. So basically I just get C times A is the height. or the area of the upper triangle, this one. And then the bottom one, the height is b, and the base again is 2c, so we have 2c times b over 2, and we just get c times b is the area of the lower triangle. So think about what c and b are. So we have c times a plus b times a, and we're going to end up, basically we can factor out a from those, and c times a and b I wrote it wrong. C times a plus c times b. So we can factor out the c and get c times a plus b. Well, if you look at what those represent, a plus b is one of the diagonals. So we could say diagonal 1 is a plus b, and then that's times c, which is half of the other diagonal. So we have the product of the diagonals divided by 2, and this is either written as 1/2 d1 times d2 or d1 times d2 over 2. They all mean the same. Similarly, triangle sometimes is written bh over 2. It means the same thing as 1/2 base times height. So you can see that it comes from triangles and is really similar in idea in that you have just 1/2 of the product of those diagonals. So that's our formula that works for that one. And of course, it also works for a rhombus and a square. So you can find the area of a square using its side lengths, like we did in this first example up here. But you can also find the area of a square as the product of its diagonals divided by 2. So this kite formula works for kites and anything below them in the family tree, so kite, rhombus, and square. The last one to talk about here, which I think we can do in our remaining room, is trapezoids. There's a few ways to think about a trapezoid. So this is any trapezoid, not necessarily isosceles. Isosceles is really simple because we can cut off one end and move it to the other like a parallelogram. But this is going to be for any kind of trapezoid. And we have basically let's make this longer. Okay, so we have a trapezoid. And a trapezoid is made up of 3 kind of primitive shapes within it, which is a rectangle and 2 triangles. So we can basically break it apart into those 3 pieces and then construct the overall area. I think we might need a little more room for this, so let's go ahead and erase a little before we try to do a trapezoid. So let's erase our triangle and parallelogram and make a little bit more space to work with. All right, back to pen. Okay, so a trapezoid is really similar to how we looked at a kite. We're going to take this kind of irregular or non-isosceles trapezoid, and we're going to draw these 2 altitudes, which have a measure of the height of the trapezoid, and we're going to break this down into 3 shapes: shape 1, shape 2, and shape 3. And we're going to call this base that they all share x plus y plus z, so that we have a way to name those 3 individual parts of the base. That's a z, not a 2. There we go. So let's look at the individual shapes. Shape 1, which is a triangle, would be x times h over 2, because it's 1/2 base times height. Shape 3 would be z times h over 2, because it's a triangle. And the middle shape is a rectangle, so its area would just be y times h all by itself, because that's the area for a rectangle. Now what we can do, just like we did on the kite, is factor out the h from all 3 terms. So we can put h times, and then we'll have x over 2 plus z over 2 plus y. And now, just like we did with the kite, we want to reframe x, y, and z into things that are actually meaningful for the trapezoid. So I'm going to call the shorter base B1 and the longer base down here B2. So we have y is the same as b1, and then x plus z is the same as b2 minus b1. So let's kind of rewrite this. We have h, and then x plus z is b2 minus b1 over 2. B2 minus, yeah. And then we have plus y is just b1. So now we could like call this 2b1 over 2 just to make it like a common denominator. So h times b2 minus b1 plus 2b1 all over 2. So we just multiplied this term by 2 on top and bottom to give it a common denominator. And so we end up with what we have as our final form. It's the height times b2 plus b1, which I'll write b1 plus b2, divided by 2. So the height times the average of the bases is how we come up with the area of a trapezoid. And it can be written in multiple ways. So b1 plus b2 over 2h is sometimes how it's written. You can do it like I wrote here. It doesn't matter, but it's the idea is it's the average of the bases times the height. Yeah, and then the last shape to talk about is a circle. Circles are kind of unique because their area and perimeter are determined by pi. We defined pi to be the ratio of the circumference to the perimeter, to the circumference to the diameter of a circle. So I'll put circle here in the middle as our last shape. And we already know these formulas and we've reviewed them in chapter 10. But perimeter we call circumference, and it is 2 times pi times r, or pi times the diameter. And then the area is going to be pi r squared, or pi d squared over 4. So those are our two ways of representing a circle's area. Yeah, so that's a review of all the basic shapes we should already be familiar with, hopefully. And those, you can use formulas for those, but I do want you to understand where they all come from, that we kind of followed a journey starting from our square here, building it up into a rectangle, breaking that rectangle down into a triangle, and then building back up all the other shapes out of those triangles. So that's our recap for that. There's some practice here that we can look at. I'll do a few of them just to go over it. And you have separate practice in your booklet. So for a square, we just do 8.5 squared, which is 8.5 times 8.5. Since I'm not using a calculator for this, I'm going to reframe this as 17 halves. And then I can say that since that doesn't simplify, when I square it, I'm going to get 289 over 4. And my units are going to be in square feet. So remember that area units should always be a square of linear units. The second one, we have a base of 15 and a height of 21.3. So we have 15 times 21.3. That would be a parallelogram, so we need to divide by 2 to form a triangle. And then since nothing simplifies here, we're going to multiply it out. We need to multiply by 10 to get this to be a whole number. So let's make this 213 over 20. Then we can simplify 15 over 20 is 3/4. So I have 3 times 213 over 4, so that's 639 over 4, and my units would be square meters. As usual, if you want to use a calculator and estimate these as well, just to get an idea of what it is as a decimal number, I think that's a great idea. So like this one would be 72.25, this one would be, oh, I don't know, 15, 159.75. So you can use a calculator or not if you want to like come up with decimal approximation. So this is about, no, not about, it's exactly. Yeah, these are exact. You can put these, so you can put these as fractions or decimals, improper fractions or decimals. And if you need a calculator to convert it, you can use that. That's okay. So this is 72.25 square feet. And this was, what was it? 159.75 square meters. Next one is a parallelogram. So we just do the base times the height. So we have 12.9 times 7.1. Use parentheses so we don't confuse decimals with multiplication. So we guess we need to multiply this by 100 in order to make it into like a improper fraction. So we could call this 129 times 71 over 100, which doesn't simplify. So we'll end up with some number of hundredths. That'll be easy to turn back into a decimal if we need to. So 129 times 71, 129, 71. So we've got 129, and we've got 6309. So 9159 over 100, I think. 9159 over 100 square inches, or as a decimal, that would be 91.59 square inches. So yeah, and then we have a circle. This has a diameter of 26. So to find the area, we would use pi d squared over 4, or divide this by 2 and do pi r squared, where r is the radius of 13. In this case, that's probably simpler to do. So we can do pi times 13 squared. We'll leave that as a precise answer, not like estimating pi. So we'll have 169 pi, and our units are square yards. So hopefully you get the idea there how to do those. So we've done square, parallelogram, triangle, circle. This one is a trapezoid. So let's look at this one. So we're going to draw in our altitude here. So we know that we add our two bases and average them. So basically we want the number halfway between 19 and 27, which is 23. And then we're going to multiply, yeah, that's the average. So I'll do it using the formula. So 19 plus 27 over 2 times the height, which is 16. Notice they've given, well, I'm assuming this is a trapezoid. Maybe it's not a trapezoid. Now I'm not sure. Let's see. They didn't indicate that these bases are parallel. We could find the area of this triangle by using 1621 and the fact that it's a right triangle to find this. So I guess we can figure out if it's a trapezoid. So this side length x right here would be, we could use Pythagorean theorem, and we could use our difference of squares shortcut in order to do 37 times 5. So that's square root of 185. Okay, that does not seem like it's gonna. Okay, whatever. So square root of 185 is that length. And then we've got 27 minus that is this length. And that would give us a rectangle, I think 27. So root 185 is about... let's see, 144, 16. So it's a little more than 13. Yeah, so it's between 13 and 14. So that means that this side is also between 13 and 14, which is shorter than 19, meaning there is a triangle right here that we can create with this altitude. They still haven't told us that the bases are parallel. Interesting. I think we have to assume they are. I don't know how you would do this problem if I don't think it's fully constrained. Maybe. I'm going to leave this one for now. So what I'm thinking is this one is 27 minus root 185. Then we have that part of 19 here, which is like 13 or 14. And then there's going to be a bit left over. And we could use Pythagorean theorem to find the height here. So we have 16.5 and then this y length here. And we could find the height here and see if it's the same. It doesn't seem like it could be, though. So I'm guessing they're wanting us to assume these bases are parallel, but they don't show us that they are, I don't think, unless I've covered it with all of my rambling. Let's see. Nope. So there's an important difference between number 5 and, say, number 10. So on number 10, they give us these two right angles here, meaning that we know the bases are parallel, whereas in problem 5, they don't give us that. So give me one sec. Okay, I wanted to check this, so I just went and drew it real quick. So this is what that shape looks like, and while it's very close to parallel, so I'm guessing that with rounding, it was intended to be parallel, but because of the rounding and the fact that we have all these dimensions, there's actually a 1.4 degree angle between the two bases. So this shape is not a trapezoid, and overall, this is just not a very good problem. We could solve it the way that I was trying to work it out, where we're using like a lot of square roots, and if we're not using a calculator and doing intermediate rounding like we shouldn't, the answer was going to be incredibly difficult and ugly to come up with. So yeah, we're going to leave that alone. And as our example for trapezoids, we're going to skip number 5. We're going to go down to number 10. Number 10 is nice because we know the bases are parallel because of these two right angles. So here we can use our trapezoid formula or understanding and say that it's the average of the bases, which should be 10, times the height, which is given as 5. So remember here that the height is the distance between the bases, not necessarily vertical on the page. So this thing is kind of rotated 90 degrees counterclockwise from our orientation of looking at 13 and 7 as the bases. So we have 7 plus 13 is 10, well, divide by 2 is 10, times 5 is 50. So we get 50 square millimeters. That one works out really nicely. Remember that instead of 7 plus 13 over 2, you can also say what's halfway between, what's the average of 7 and 13, and say that 10 is halfway between, kind of like a midpoint. So you can use the either way, either averaging or finding the midpoint of 7 and 13 in order to come up with this part of the formula. And then the last one, just because it's different, we have here a semicircle. So a semicircle is going to be just a circle, but half of it. So we have pi r squared, and we divide that by 2. So 17 squared is 289, so we get 289 pi over 2 square feet. And if we wanted to turn that into a decimal, that would be 144.5 pi square feet. So yeah, that's hopefully all a recap. I don't think there should be anything new in what we have covered today. So tomorrow we'll get into composite figures, which you've probably seen a little of, but the idea of taking smaller shapes, adding them together, and coming up with bigger shapes.